So 10.1.3, definition of an exponential function. In example 4, we're asked to evaluate the expression 3 times 2 to the t for t equals 0, 1, 2, 3, and 4. Okay, so evaluate is another one of our verbs that we've seen a lot this semester, and that just basically tells us to do the math, follow order of operations, until we get a single number for an answer. So the expression they give us is 3 times 2 to the t, and just like before, we're going to put parentheses around our variable before we substitute. So we're going to get 3 times 2, and for t we're going to substitute a 0. Okay, from the previous page of notes, we know that 2 to the 0 power is 1, so this gives us 3 times 1, which is 3. Okay, exponents happen before the multiplication, so following order of operations, we did the math until we got to a single number. Now if we take this same expression and we're going to substitute 1, and then we're going to substitute 2, and then we're going to substitute 3, and finally we're going to substitute 4 for t. So 2 to the first power is 2. Again, exponents happen before the multiplication, and 3 times 2 gives us 6. 2 squared is 2 times 2, is 4, so 3 times 4 we get 12. 2 cubed means we have 3 factors of 2 all being multiplied together, so 2 times 2 times 2, which is 8, and 3 times 8 is 24. And finally 2 to the 4th, so 4 factors of 2 all multiplied together, so we have 2 times 2 times 2 times 2, which is 16, and 3 times 16 is 48. So below is the data from the first page of these lecture notes. And we're asked what we notice about the outputs below. So that would be these. Okay, so we've got an input-output table, so these are our inputs, and these are our outputs. And the answers you got in example 4, which are up here. So the answers we got here were 3, 6, 12, 24, 48. The outputs we got here were 3, 6, 12, 24, and 48. So we should notice that they are the same. Okay, or that they match. So the relation between time elapsed and number of bacteria, so time elapsed, okay, that was our input, and number of bacteria, this was our output, there's our 2 variables, can be described with the following function. So the number of bacteria at time t is 3 times 2 to the t. Okay, that was the formula that worked for each of these inputs, gave us exactly the output that we had in the table. So this leads us to a new family of functions for this particular unit. So an exponential function. An exponential function is a function whose equation can be put in the form f of x equals a times b to the x. And so actually if we want to write this, these are mushed together, but this is really an a times b to the x. Okay, a cannot be 0, and this base number, we're going to see as we're looking in the table what we keep multiplying by is some positive number, and that base cannot be 1. Okay, so if we look at the table of data above, and the function n of t equals 3 times 2 to the t, describe how these constants a and b are related to the patterns in the table of data. Okay, so if we go back up to this table, we noticed on the first page that as we kept increasing our inputs by 1, our outputs over here kept being multiplied by 2. And we can see that here too. 2 to the 0 was 1, 2 to the first power was 2, it's doubled, and our answer doubled. And then here we had 2 squared, okay, so again it doubled again, and then 2 cubed, it doubled again, and so on. So this base, this number here, 2, seems to be what we multiplied by. So these were what outputs multiplied by when x increased by 1. But now what about this 3? So here, this is our initial number of bacteria at time t equals 0. So just like with linear functions, okay, we looked at kind of an initial value and then how much it increased or decreased by. The same thing here. So we have this initial value when t equals 0. And then again, this base here gave us what was multiplied, what we kept multiplying those outputs by as x increased by 1. So let's compare linear functions to exponential ones. How they look pattern-wise different, and then how that's expressed differently in their equations. So in this particular set of data, our input variable x kept increasing by 1, and we can see that our outputs here keep going up by 2. Constant change in input leading to constant changes in output tells us that we have linearly related data. Okay, which means that we have, this f of x equals, some constant. So when we looked at the calculator, or we'll use the notation from algebra, like b plus mx. Okay. Or mx plus b, but in class I've been writing it this way to emphasize our initial quantity and then how much it went up or down. So in this case, our initial starting point was 3, and then we kept going up by 2 for every unit increase in x. Okay, so here we've got addition, because our outputs we kept adding on 2. And here, this is multiplication, but we use that multiplication to represent the repeated addition. Now I want to add 2 and add 2 and add another 2. So to get from 3 to 9, I really want to add on 3 2's. And well, we can do that with multiplication. Instead of add 2, add 2, add 2, we can add 2 times 3. But now this new pattern, as we keep increasing x by 1, over here, instead of adding or subtracting like we did with linear functions, okay, over here, we are multiplying by 2 each time. Okay. This is going to be what we're looking for to say that we have exponentially related data, meaning that we can describe this relation with an exponential function. Okay. All right, so we have this kind of initial starting quantity and then our base multiplier that we're using. So in this case, it started at 3 and it kept doubling. So here we can see that we have multiplication. To get from one output to the next, we kept multiplying by 2. And then here we have an exponential piece, 2 to a power, but again, that's our shorthand notation in mathematics for repeated multiplication. So again, we should recognize the difference in the patterns between linear and exponential, and then again, how that's going to be represented differently in how we describe that relationship with the function notation.